is going to generate tensile, so this is plus. Our reference material was brass, so this is 1. And then we calculate moment about Y is 375. And then we did calculate the IYY. So IYY is 2.859 times 10 to the power minus 6. The next point where a lot of students make mistake is the Z. Okay, so from here, we want to calculate the Z distance. At point A, can someone tell me what is the Z distance, please? Anyone? Is it 123.205 or is it 150 divided by 2? So if you're not sure, just remind yourself that this is the Z direction and this is the what? This is the Y direction. So when that's the Z direction is equal to 0.15 divided by 2. This is important. A lot of times students make mistake at this location. Are we clear? Right? Because there's so much factor in here already and you can get pretty what? Confused. Then if you look by moment about Z at point A, it's also going to be what? So this is moment about Z now. At point A is going to be what? Tensile. Right? So this is going to be what? Positive. And this is going to be 1. And then you have 1717.936 times 10 to the power 3 divided by IZZ. IZZ is equal to 65.694 times 10 to the power minus 6. Now, what is this distance? It's the Y distance. So it's equal to what? 123.205 times 10 to the power minus 3. Okay, so when you compute that, you will get 0.707 times 10 to the power 6 plus 375 times 0.15 divided by 2 divided by 2.859 power minus 6 is equal to 9.837 and then plus 1 times 17.936 power 3 times 123.205 power minus 3 divided by 65.69. So this will be equal to 33.638 times 10 to the power 6. Okay, so 0.707 plus 9.837 plus 33.638 is equal to 44.182 positive times 10 to the power 6 Pascal. So the next thing that we do is you also calculate what? Point B. But now, listen to me. I'm doing point B is just at how to analyze point B. In the test, do you need to calculate point B? The answer is no, you're right. Okay, why no? Okay, so I'll show you why. So stress X at point B, axial load is still the same. Am I right? Now, if you look at moment about Y now, moment about Y will generate what? Compression. Am I right? I repeat again, moment about Y will generate compression. And because the Z distance is the same, you can put minus 9.837 times 10 to the power 6. Moment about Z is still what? Tensile, yes or no? So plus by what? 33.638 times by 10 to the power 6. So this will be equal to 0.707 minus 9.837 plus by 33.638 equal to 24.508 times 10 to the power 6 Pascal. Do we need to identify the maximum compression for brass? Repeat again, do we need to find the maximum compression? At this stage, no. Later on, I'm going to teach you how to confirm your answer. Okay. Now, Do you appreciate the moment vector now? The head of the moment vector is what? Compression, the tail end is what? Tensor, yes or no? If not, you have to go into what? Matrix form. I want you to go to matrix form. Like in 2Q1, they teach you about IG and K. Clockwise, positive, and clockwise is what? Negative, yes or no? You have to visualize this as a mechanical engineer also. Okay? But there are some limitations. I'll show you the limitations later on. The next thing that we're going to do is we are going to identify, right? We are now going to look at the steel material. You're going to look at the steel material now. Okay, so I'm going to take this point. Now this figure is really important. This is your analysis figure. Okay, it's important. Once you have this analysis figure, you're good to go. Okay, let's look at this analysis figure now. Okay. Looking at this analysis figure, okay, I'm going to select 4 points. Okay, we are going to select 4 points. So this is our point I, point J, point K, and point L. Okay, these are 4 points. So you identify them as points I, J, K, L. Then we look at moment about Y, okay, and then we look at moment about what? Z. Okay. Can you fill this up and tell me how to fill this up? At point I, moment about Y will be what? Tensor. At point J, moment about Y will induce what? Compression. At point K, moment about Y will induce what? Compression. And at point L, moment about Y will generate tensor. Okay. And we look at MJ, moment about Z, right? A moment about Z at point I is going to be tensor. At point J is also going to be tensor. And at point K is going to be compression. And at point L is going to be a compression. And if we look at the axial load, they are all going to be what? Tensor. By looking at this chart, this is what we call what? We are doing what? Analysis. Are we clear? Now we are dealing with what? Analysis. That's why this figure is so. So what are 2 points that you want to calculate? Anyone? And tell me why. What are 2 points that you want to calculate? Anyone? Yes. I and K. Why? Well done. The rest of them, you can what? Ignore. Are we clear? The rest of them, don't bother. Don't waste your time. But what comes to your mind also? Will there be a neutral axis? There will be a what? Neutral axis. Are we clear? Okay, so from here, we also discover that the neutral axis where stress X is equal 0 will occur in where? In steel. Are we clear? Right? So in this context, we can ignore what? We can ignore, try to find brass material that has the maximum what? Compressive stress. Are we clear? It's not going to happen at all. Why? Because the neutral axis pass through the what? Steel material. Does that make sense? Okay, nothing to memorize. This course, don't memorize. This course is all about what? Analysis. Daniel. For what material? For the brass material? Yep, if it's given, asking you to find factor of safety, yes. Okay. Hey, don't mix up with buckling, okay? It's different ball game, yeah? Right. So from here, we are going to calculate stress max, tensile, right? And we know it's going to be at point I. So when you already have written point I, at the same time, write down what is the what? What is the y distance? Okay. So the y distance is 123.205 minus by the wall thickness of 10. So this is equal to so this is for point I, right? So 123 minus by, so it's equal to 113.205 times 10 to the power minus 3, or this is in millimeters. And then to change to meter. Okay. And then if we look at our Z distance, our Z distance is equal to what? 0.00 or 10 millimeters divided by 2, which is 5 millimeters. So 5 millimeters is equal to what? 5 times 10 to the power 3 meters. Sort this out first. Are we clear? Okay. The thing about this course is you have a lot of components coming in. Okay. Identify the key points first and write them down. Are we clear? Okay. Don't lump everything into one equation. You go crazy. When I grade, I go mad. Okay. So now we know that we are going to use stress Z. Okay. So the formula is still the same. Axial normal stress plus minus n my over iyy multiplied by z plus minus by n mz over izz multiplied by y. Okay. So we calculated our stress Z due to the normal load in steel last week is 1.359 times 10 to the power 6. Okay, so it's 1.359 times 10 to the power 6 is positive because it's under what? Tensile. Okay. Oh, sorry. We are going to find point I. Okay. So for point I, right, My is going to generate tensile, Mz is also going to generate tensile. So both are plus. So we have a factor over here. This is equal to 200 divided by 104 multiplied by My is 375. Z is equal to 5 times 10 to the power minus 3 divided by Iyy is 2.859 times 10 to the power minus 6. Anyone, any question? Are we okay? Okay. We're good, yeah? Plus, by again, this is the n value. Okay, so Mz is what? We have Mz earlier, can't remember. Mz is equal to 17.936. 17.936 times 10 to the power 3. Y is equal to 113.205 times 10 to the power minus 3. And divide by your IZZ is equal to 65.694.